Okay, good. John, I think, yeah, everybody can hear you. And yeah, so John will tell us something. By the way, John, will you start sort of with a brief background on HSDS?
Yes, I will.
Okay, great. So for those of you who haven't caught up yet on HSDS, John will give you an introduction. And yeah, John is sort of the brains and the brawn behind HSDS, the highly scalable data service. And John made lots of improvements on that over the years. And yeah, he'll tell us something exciting about HyperChunking for the cloud today. Go ahead, John.
Okay. Well, I don't know how exciting it'll be, but I'll do my best. Hey, everyone. Sorry I couldn't be there in person. Actually, Ohio State is my alma mater. But unfortunately, I wasn't able to be there in person this year. Anyway, so I'm going to talk about HyperChunking and explain exactly what that is in a minute. So we'll talk about an overview of HSDS. I've talked about it many times in previous hugs, but for those who haven't heard about it or need a refresher, we'll go through that. And then we're going to kind of narrow in on how to import HDF files into HSDS, and then talk about HyperChunking and intelligent rain gets, and how that works with the case study we're doing for NASA. All right. So HDF for the cloud. So the library has been around for quite a while, but it wasn't naturally designed with the cloud in mind. And some of the architectural decisions made aren't exactly compatible with optimizing object storage access. And when I talk about cloud storage, I'm going to say S3 a lot, and I really mean either S3 or Azure Blob Storage or Google Cloud Storage. They all work in a very similar fashion, and they're all quite different than what we're used to with POSIX storage. But the reason why it's so popular in the cloud is, one, is cost, right? So from this cost comparison between S3 and different other storage formats for the cloud, it's quite a bit cost effective. Also, the advantage of S3 is that you can access it from anywhere, right? Whereas like an EBS volume, you can only access it from that actual machine that has it attached. So we like to put HDF data in S3. And you could just download those files as you need them, but that's not very efficient, especially if you have really large files. And there actually are ways that you can read HDF files on S3 directly, but they're quite slow. And they also don't support writing. And the reason of the slowness is that compared to POSIX I/O, the latency for S3 access is quite high, ginormously high, basically. But still, you can get really good throughput with S3, but you can't get that with a bunch of serial I/O requests. You have to do fairly large requests and 8 or 16 in-flight requests at any one time to get the best performance. So given all this, we developed this new paradigm for storing HDF data in the cloud, the HDF Object Storage schema. And it works like this. You take each metadata in a file and you store that as a JSON object. And you take each chunk of each data set and you store that as a blob. So it's similar to Mark was talking about ZAR and some other efforts where you're using the file system to manage the directory of objects rather than doing those internally within the file. But unlike POSIX and the limitations that you can have with like a really large number of files in a directory, you don't have that with S3 and other object storage systems. So here's a data set, and it's chunked. So each of these chunks will actually point to a separate S3 object. And when you do a data selection, like this yellow rectangle, you're intersecting some number of chunks. So you'll need to fetch each of those S3 objects and partition the data you need, and then glue it all back together to get that selection. Which seems like a lot of work, but that's how we came to develop the HSDS. Meanwhile, here's an example of how this would look in like a directory style format. You have a metadata JSON for the root group. You have a subgroup of its group JSON. You have a data set of its JSON. And the JSON just describes things like the dataset shape and the attributes and so on. And then you have these things 0_0, 0_1. These are the keys for the different chunks of those datasets. And one thing you'll note is that it's not a format like ZAR uses, where if you have a data set that's in /G1/G1.1, the hierarchy would be like a /G1 folder and a /G1.1 folder, and then the data set. Here, we have just this two-level hierarchy. There's a root object and then the dataset objects. So they're all keyed by their object ID, not by the path name. And this allows us to do multi-linking, where you can have two links from two groups pointing to one object, for example. So you could read and write the storage format directly, but it's a lot easier to use HSDS, which is a REST-based service for HDF. So I won't go through all the details of this, but basically you interact it with directly with REST API or one of these SDKs. It runs in Docker or Kubernetes. And as the name implies, it's scalable. You can run on any size machine or in a cluster of machines. And the way it works is basically like this. You have these multi-process nodes, right? So these service nodes and data nodes. The data nodes, these green nodes, they partition the storage space. So any object belongs to a specific data node. And then the service node are the nodes that clients interact with. So the client would send an HTTP request to a service node. Service node would talk to one or more data nodes to get the requisite data it needs to do that request, and then returns response back to the client. And this is where the scalable aspect comes in, is because we can run any number of service nodes and data nodes. And if that's too much for one machine to handle, you can run it on a cluster. And this describes different platforms and different storage systems we support. So as I said, you can use the REST API. There's a Python package called H5PyD, which emulates H5Py. And for the H5 library, there's a plugin called the RESTfile. And Matt will be talking about the RESTfile in just a bit. And there's a set of command line tools. So for example, let's say you wanted to remove an HSDS air quote file. Well, there's no directory, right? There's no, you can't do rm splat. You have to use one of these CLI tools, like HSRM in this case, to delete that particular file. So that's all very good. But what if I have, say, a repository of HDF files and I want to use HSDS on them? Well, one alternative is use one of these command line tools called HSLoad. And you say HSLoad this file to HSDS, and it gobbles up all the data and sends it to HSDS. And now that data is available on the server. It's interesting to point out, as during this process, we may optimize the chunk shape of the data sets, because it turns out that something like 1 to 4 megabytes per chunk is optimal for cloud access. There's no alternative, though, called HSLoad-link. And here, you're assuming your file, your HDF file, is already in the cloud. You want to just extract the metadata and leave the chunk data where it is. So HSLoad-link will extract the metadata and create pointers to all the chunks in each data set in the file. So here's an example. You have your dataset metadata, and we create these indices for each chunk, and it points to somewhere in the file. So a chunks for a particular data set may be sequential within the file, or they may be scattered. There's really no way to tell beforehand. how they'll be arranged. So the problem, though, with this chunk linking is that we find many files actually have chunk sizes that are smaller than 2 to 8 megabytes. And then when you try to access those through HSDS, the format is not so good. For one thing, the SN to DN connection, there'll be a lot of requests from the service node to the data nodes because each chunk access is a separate HTTP request from SN to DN. While you could reformat the file to be larger, to use larger chunk sizes, that can be a quite tedious and expensive process. So on to HyperChunking. The idea of HyperChunking is that we use a larger chunk size in the HSDS model than we have in the HDF5 dataset. So we gather multiple HDF5 chunks in the file and create this virtual HyperChunk. So for example, if your H5 chunks are 40 kilobytes each, we would take 100 of those, lump them together, and that becomes one HSDS HyperChunk. So now we reduce the number of requests that the SN nodes need to send to the DN nodes to retrieve a particular chunk. But still, and the DN nodes, once they get the request to read a HyperChunk, they can figure out which S3 range get requests are needed to retrieve the actual HDF5 chunks from the HDF5 file. So it would look like this. You may say, take 2 by 2 H5 chunks and create one HyperChunk. And each of these H5 chunks will be contiguous in the sense of their contiguous chunk indices, maybe not actually contiguous within the file itself. And each H5 chunk has a unique offset and size so that HSDS can reach in and do a range request to pull out that chunk without actually going through the HDF5 library. So the process would be like this. Say the SN node receives request for a dataset selection. It determines which hyperchunks intersect with the selection region. It would send a DN request for each hyperchunk. On the DN side, it would fetch all the H5 chunks to fill a given hyperchunk. It would store the hyperchunk in the DN chunk cache, then do the selection for that chunk, that hyperchunk, send the data back to the SN node. The SN node aggregates all responses from the DN nodes and sends that response back to the client. So that's all very good. And now we reduce the number of SN and DN requests. But on the DN side, for a hyperchunk, the DN node is still doing a bunch of S3 requests for each of the H5 chunks. So it often happens, though, that within a file, these H5 chunks, so recall that the H5 chunks for HyperChunk are usually sequential chunk indices. And it often happens in the HDF5 file that these chunks are actually contiguous within the file space. So here we use what's called this intelligent range get, right? We glump up those chunks and make one S3 request to retrieve a set of contiguous H5 chunks, and that reduces the number of S3 requests involved. If it's not possible, we do a bunch of asynchronous S3 requests, which also works pretty well. So finally, let's see how this works in practice. So NASA has a mission called ISAT-2, which collects very detailed height measurements as the satellite orbits Earth. And each ISAT-2 file is about 3 gigabytes with 1,000 datasets per file. And as we see, it has a very small chunk shape, like usually 80 kilobytes per chunk. So using this directly with the ROS3 VFD or HSDS does not work very well. Rechunking, since it's petabytes of data, is not practical. How does HyperChunking help? So here, the original chunk shape was 10,000. The chunk size was 39 kilobytes, or 3,000 some chunks. In an HSDS version of this data set, the chunk shape is 320,000. The chunk size is 1.2 megabytes. and there's 115 HyperChunks. And the performance works like this. I'll go backwards. With ROS3, it took 99.5 seconds to iterate through the entire data set. With HSDS, using 1-1 chunk linking, it took 44 seconds. With HyperChunking, it took only 12.5 seconds. So basically a 4-to-1 improvement over 1-1 linking, and 8-to-1 improvement over using the ROS3 VFD. And one last thing I'll point out is that utilizing a chunk cache, you get dramatically faster performance, right? So once you've loaded this file into HSDS, if you do the same application again, since the chunk cache is persistent across multiple runs, we get times of like 5 seconds and 2 seconds each. Okay, so conclusion, we love HyperChunking. I'm not sure it solves every problem, but I think it's a useful tool to have. And also pay attention to chunk cache, right? If you have a problem where your working set is relatively small, as in small as like a few hundred gigabytes, then you can potentially keep everything inside cache and you'll have really fast performance. And this was sponsored by a NASA contract. And that's it.
All right. Thanks, John.
So any questions?
Yeah, I think we have time for one question. Are there any questions for John? No questions, John. Sorry.
No questions. Oh, okay. All right.
Oh, Mark has a question. Yeah.
Okay.
Okay, here's the question.
Okay, hi, John. I think you've been mostly presenting the HyperChunking as kind of a legacy feature to support, unrechunked HF5 files. But I'm wondering if we're going to intend to use it for maybe things that were more naturally chunked in smaller files, if a different kind of chunk order would facilitate this. Namely, could we use a Morton C space filling curve instead of kind of like C or F order chunks, so that you could more naturally create hyperchunks just by virtue of chunks that are closer together being closer together in memory? Is that
right? I think so. If you, I guess in general terms, this chunk linking is basically indirection from that region of a data space to a particular piece of data somewhere. So you could use that indirection to set up any kind of ordering you want, right? That may be more natural in terms of the type application you're using.
Right, because I noticed the SAR shard specification, this is a CEP2, is adopting a Morton order as kind of preferred order of chunks. And I'm thinking you're starting to converge in similar solutions there.
Right. Yeah. It's funny, speaking of ZAR, is that, it's obviously very similar, like the HSDS sharded format and the ZAR format. And we arrived at this at virtually the same time. And I think it's just the nature of trying to solve this particular problem for cloud storage. It makes sense to utilize this kind of structure.
Great. Thank you.
Okay, thanks, John. And by the way, John is a regular host on our Tuesday HDF clinic. So if you have any other questions about HSDS, just meet John there and he'll be happy to answer your questions.